back again. This is going to be part 9. And it's going to be episode 28 of Learning by Doing MPI. We are still talking about chapter 7 of MPI, which was about groups, contexts, and communicators and caching in MPI. We're going to continue from where we left off in the last episode. We talked about caching in communicators and adding, setting attributes and retrieving them with getting, the cousin sort of operation. And now we want to talk about the same sort of functionality, but in data types. We said that caching basically operates in 3 areas of communicators, windows, and data types. We skipped windows, and now we want to talk about data types. So we have, you remember we had MPI create keyval. So this one is about data type. So that is why we have MPI type create keyval. So the syntax only changes because of that. And then everything is the same. So we have this sort of type copy attribute function, and then we have type delete attribute function, and then you don't have the com keyval, but you have type keyval again to basically stress the fact that this is an attribute corresponding to types. And then we have that void star extra state as well. Again, everything is going to be in, and then you're going to have an output, which is the type keyval or that attribute that you want. Okay, again, here these things are going to have a little bit of strange type. Previously, it was MPI copy attribute function, but here it's MPI type copy attribute function. It's in star as well, so it's a function pointer type, and for delete as well, it's going to be a function pointer type. And similar to, let's say, communicator one, it's going to have a type def, which has this signature of basically those callback functions. This is for the copy operation, and this is for the delete operation. The copy one is going to get activated once you are using those duplicate operations. In the case of communicator, it was com dupe, com idupe, com dupe with info, com idupe with info. And in the case of let's say types is MPI type dupe. That is basically the duplication. And the deletion is basically when we free those resources that we have allocated. And last time I also forgot about this last thing, that the extra state, this delete statement goes to 0. It's because that once we have deleted this attribute, once we have freed that attribute, then before printing this stuff, I try to also decrement my extra state, which, as I said, I use it as a counter. So the duplication made it from 0 to be 1 with this +1 operation, and then once I free the stuff, I decrement it to 0. 1 minus 1 is going to be 0, and that is why we ended up with this value as well. I forgot to comment on that. And then another comment which I forgot to mention is the freeing section. We didn't talk about that. So as I said, normally you don't need to care about this MPI delete attribute, because finally, once you're done with your communicator, you are going to free your communicator. So that is why I put MPI free dupe original communicator and original communicator, because in these two sort of operations, that delete callback function is going to automatically get called. So you don't need to explicitly put this MPI delete attribute. But if you want to do that, then always you need to make sure that MPI delete attribute comes first or comes before than MPI free keyval, because this one depends on keyval. So if you free the keyval first, then you're going to see a lot of strange errors happening in MPI. So that is why I put this sort of comment here. Does the order matter? Yes, it does. If I uncomment this thing, this MPI delete attribute has to be always before MPI free keyval. Okay, this was another point which I forgot to mention. But for types, as I said, everything looks similar to what we had in communicators. I'm not going to comment on these because we have already seen these. If an attribute copy function or attribute delete function returns other than MPI success, then the call that caused it to be invoked, for example, MPI type free, is erroneous. Yeah, we had seen that one also for communicators. And then we have the corresponding free operations for that attribute. This time is marked with type, so it's MPI type free key val instead of MPI com free key val. You pass in your attribute, and then yeah. And then we have the set attribute, similar to com set attribute, and then corresponding to that we have this get attribute to retrieve that attribute. And then we have, if you want to explicitly delete sort of an attribute from a data type, you can use this MPI type delete attribute. I'm going to pass these so fast because we're going to see an example for this one as well. So we have MPI type create key val. What do we have? Oh, we have simple and advanced. Okay. In the simple version, again, everything is sort of having the same flow with the communicator version. So for the simple version, the copy callback function is going to be simply associating this with attribute val out, attribute val in with attribute val out. We set the flag to be 1, and then we return MPI success. And for MPI delete, so I always say MPI for type delete attribute function or the delete callback function, we do nothing and return MPI success. So now I need to add this do nothing and return MPI success. I forgot to add that. Then everything is more or less the same flow as I said. You have a type key val, it's a type attribute, and then the value you want to assign to that is 42. And then you create that key val or that attribute. You pass in your copy callback function, delete callback function. You pass in your basically attribute, and then you pass in. You don't want to use your extra state sort of variable. You pass in null here, and then you need to create a data type. If you don't know how to work with data types in MPI, please go back and watch the episode related to data types in MPI. Which was the subject of chapter 5, if I'm not mistaken. And then we create a new type, and then we use MPI type contiguous constructor. We want 2 integers to be basically connected to each other, and then that's going to be our new type. We commit our type. You remember that always you need to commit your types before you use them. And then we want to set that attribute, but not to that communicator, but to the data type that we have generated. We pass in our data type, and we pass in the attribute, and then we pass in the value which we want to assign to that, which was 42. And then what we do is that we create this void start attribute value. We create a flag, and then we retrieve that with get attribute operation. As I said, this MPI type get is the cousin of MPI type set, but it has a flag extra here. And the reason for that is once you want to set, you set no matter what happens. But once you want to get an attribute, you need to make sure that the attribute even exists. So that is why we do have this flag. So you just print that thing, and then you duplicate your data type with dupe new type, and then you change that value from 42 to 7. Then you do the same thing, basically. You check the dupe new type and see what attribute value it returns after you change this value to 7. And then you change, you do the same MPI type get attribute for new type, which was the old type actually. And finally, in the end, you need to do freeing. The same comment goes also here, MPI type delete attribute. Usually you don't need to explicitly do that. Because once you call this MPI type free, then those delete callback functions are going to call automatically. And does the order matter? Yes, if I uncomment this line, then this has to be always before this free key val, because this one depends on that. So let's go back and MPICC, MPI type, create key val simple. And let's run it with 9 processes. You see that the value the first time is 42. After I change the value from 42 to 7, dupe new type is going to return 7, and new type is also going to return 7. Now the same drill also goes for MPI type create key val advanced, but this time we dynamically allocate a memory for that. Everything is similar to what we had for communicators. So we use our extra state variable as a counter here. For delete callback function also, we check that extra state or the counter first, and then we free that attribute, and then we try to decrement that extra state or that counter. And then we return also MPI success. And the only change which happens down here is that we add a counter and we add a void star extra state, and we pass in the address of that sort of integer into that. So that's the only thing. And if we do MPICC, MPI type create advanced, and we run it with 9 processes, you see that this time instead of having 7 for dupe new type, we have our own copy in this dupe new type, which still is unchanged, and the value is 42. Whereas the new type, which is actually the old type, it's not the dupe new type is the new type. This one holds the value of 7 because we changed the value from 42 to 7. Okay, easy stuff. Then there's an example here, which we don't care about that. The next section is a short section. We don't have any examples for this one because this is also, again, very straightforward. It's naming objects, and you don't have to name your objects, but it is usually good for the purposes of so let's see, there are many occasions on which it would be useful to allow a user to associate a printable identifier with an MPI communicator window or data type, for instance, for error reporting, debugging, and profiling. So for these purposes, it's a good idea to name your basically objects. The names attached to opaque objects do not propagate when the object is duplicated or copied by MPI routines. And for communicators, this can be achieved using the following 2 functions. So you have, again, 2 cousins, MPI com set name and MPI com get name, of course. You pass in your communicator, and then you pass in your name. The name is, of course, it's a CS style string. It's a const-char style. I think it's straightforward. I don't have any examples for this one. And it says MPI set name allows a user to associate a name string with a communicator. The character string that is passed to MPI set name will be saved inside the MPI library, so it can be freed by the caller immediately after the call or allocated on the stack. Leading spaces in name are significant, but trailing ones are not. MPI set name is a local non-collective operation which only affects the name of the communicator as seen in the MPI process that made the MPI set name call. There's no requirement that the same name, or any name even, be assigned to a communicator for that matter in every process, in every MPI process where it exists. Then MPI get name, again, you pass in your communicator, you pass in the name of that thing, and then the resulting sort of value, the result length is going to be, so the name is going to get retrieved into this com name, and the result length is the length of the return name. That's how it looks in C bindings. You pass an MPI communicator. It's a char star for the name, and it's going to be an int star for the length. Again, I put an X here because we have already seen these over and over. We have a rationale here. We provide separate functions for setting and getting the name of a communicator rather than simply providing a predefined attribute key for the following reasons. It is so. Here's the drill. It says that we provide separate functions for setting and getting the name of a communicator. So why didn't we use sort of predefined attribute keys for that? Because we had that caching, right? We were talking about that set attributes, get attributes. Why do we have a separate routine for that? The reason for that is the following. It is not in general possible to store a string as an attribute from Fortran. It is not easy to set up the delete function for a string attribute unless it is known to have been allocated from the heap. To make the attribute key useful, additional code to call strdupe, that's a C sort of call, is necessary. that's a C function, sorry. If this is not standardized, then users have to write it. This is extra unneeded work that we can easily eliminate. And a Fortran binding is not trivial to write. It will depend on details of Fortran compilation system and will not be portable. Therefore, it should be in the library rather than in user code. So that is why we have this as well. And advice to users, the above definition means that it is safe simply to print the string returned by MPI getName, and it is always a valid string even if there was no name. Okay. So corresponding to communicators that you can set names, you can get names. Again, here you have the ones for data types. That's MPI type set name. Same drill, MPI type get name. And same sort of routines also exist for Windows, which we don't care about them for now. Okay, that's basically the final remarks. It's a few paragraphs here, and then this chapter is completely over. Let me see how many minutes do I have. I have 8 minutes. Maybe we can read this section as well as fast as possible. So it says formalizing the loosely synchronous model. In this section, we make further statements about the loosely synchronous model with particular attention to intra-communication. Basic statements. When a caller passes a communicator that contains a context and group to a callee, that communicator must be free of side effects throughout execution of the subprogram. There should be no active operations on that communicator that might involve the MPI process. This provides one model in which libraries can be written and work safely. For libraries so designated, the callee has permission to do whatever communication it likes with the communicator, and under the above guarantee knows that no other communication will interfere. Since we permit good implementations to create new communicators without synchronization, such as by pre-allocated context on communicators, this doesn't impose a significant overhead. This form of safety is analogous to other common computer science usages, such as passing a descriptor of an array to a library routine. A library routine has every right to expect such a descriptor to be valid and modifiable. Models of execution. In a loosely synchronous model, the transfer of control to a parallel procedure is effected by having each executing MPI process invoke the procedure. The invocation is a collective operation. It is executed by all MPI processes in the execution group, and invocations are similarly ordered in all MPI processes. However, the invocation need not to be synchronized. We say that a parallel procedure is active in an MPI process if the MPI process belongs to a group that may collectively execute the procedure, and some member of that group is currently executing the procedure code. If a parallel procedure is active in an MPI process, then this MPI process may be receiving messages pertaining to this procedure, even if it doesn't currently execute the code of that procedure, okay? So we have two models, a static communicator allocation, dynamic communicator allocation. This covers the case where at any point in time, at most, one invocation of a parallel procedure can be active at any MPI process, and the group of executing MPI processes is fixed, so it's not going to change. For example, all invocations of parallel procedures involve all MPI processes. MPI processes are single-threaded, and there are no recursive invocations. In such a case, a communicator can be statically allocated to each procedure. The static allocation can be done in a preamble as part of initialization code. If the parallel procedures can be organized into libraries so that only one procedure of each library can be concurrently active in each processor, then it is sufficient to allocate one communicator per library. In a dynamic case, calls of these parallel procedures are well nested if a new parallel procedure is always invoked in a subset of group executing the same parallel procedure. Those MPI processes that execute the same parallel procedure have the same execution stack. In such a case, a new communicator needs to be dynamically allocated for each new invocation of a parallel procedure. The allocation is done by the caller. A new communicator can be generated by a call to MPI dupe if the callee execution group is identical to the caller execution group, or by a call to MPI split if the caller execution group is split into several subgroups executing distinct parallel routines. The new communicator is passed as an argument to the invoked routine. Okay, the need for generating a new communicator at each invocation can be alleviated or avoided altogether in some cases. If the execution group is not a split, then one can allocate or stack allocate a stack of communicators in a preamble, and next manage the stack in a way that mimics the stack of recursive calls. One can also take advantage of the well-ordering property of communication to avoid confusing caller and callee communication, even if both use the same communicator. To do so, one needs to abide by the following two rules. Messages sent before a procedure call or before a return from the procedure are also received before the matching call or return at the receiving end. Messages, the second rule is messages are always selected by source. No use is made of MPI any source. Okay. So you can read this paragraph. It's I don't care about this one. That is basically the mark of the end of chapter 7, which was about groups, contexts, communicators, and caching in MPI. I do hope that you learned something from this all these series of videos, and hope to see you in the next one.